Hello again, and welcome to our lecture on inverse trigonometric functions. I hope you've enjoyed the last few lectures developing trigonometry. You'll remember that we defined the trigonometric functions and we learned how to evaluate them for various angles, not only acute angles, but any angle, positive or negative. And then we had some fairly difficult lectures on graphing trigonometric functions. I'm the first to admit that's a non-trivial skill, but keep in mind the sine and cosine have that wave motion, and also keep in mind that unusual tangent graph. We'll be seeing it again today. Well, what about these inverse functions? You might recall a few lectures ago we developed the logarithmic function as the inverse of the exponential function. The exponential function was a rising exponential curve, and you remember it passed the horizontal line test. It was a one-to-one function, and hence it had an inverse. So we'd like to do the same for the trigonometric functions. We'd like to find their inverses. So think in your mind a moment, what do the graphs of the trigonometric functions look like? Here's sine, cosine, tangent, etc. And you might immediately say to yourself, it's not going to work. Why not? They aren't one-to-one. They don't pass the horizontal line test, do they? Horizontal lines can hit the graph of, say, the tangent function or the sine function more than once. In fact, infinitely often. So what do? How do we define these inverse trigonometric functions? Well, the key is to restrict the domain of the corresponding trigonometric function to a little piece of the graph. And on that piece, the function will be one-to-one. Okay, let's start by, say, looking at the most important inverse trigonometric function, the inverse sine function. How does it go? How do you develop the inverse sine function? Well, you start with f of x equals sine x, the graph of the sine function. And here's a picture of it. And again, it's not a one-to-one function. Horizontal lines can hit many, many times. But if I restrict the domain to the closed interval minus pi over 2 to pi over 2, on that little interval, you see that the function is one-to-one, and hence it has an inverse. And the inverse is called the inverse sine function, sometimes called arc sine. I prefer that word arc sine, but both are used interchangeably. So what would the definition of the arc sine function be? Well, the domain of the sine function, the restricted sine function, is minus pi over 2 to pi over 2. That will be the range of the arc sine. And the same way, the range of the sine function is minus 1 to 1, and it still is that range when I restrict the interval, and that will be the domain of the inverse sine function. So here's the formal definition of the inverse sine function, or arc sine. Why is arc sine x if and only if the following is true? Sine y equals x. Well, of course, that's always the definition of an inverse function. But you have these domain and range restrictions. The domain of arc sine is minus 1 to 1, and the range is minus pi over 2 to pi over 2. Again, why are these restrictions there? Well, remember, the range of the sine function was minus 1 to 1. That becomes the domain of its inverse. And in a similar fashion, the domain of the restricted sine function is minus pi over 2 to pi over 2, and hence that becomes the range of arc sine. Again, that notation is y equals arc sine x, or sometimes you'll see it written as sine inverse, a little minus 1 of x. Okay. On a calculator, I've looked at calculators, various brands. Some have arc sine on the key, and others have sine inverse. And in fact, the button for the inverse sine is usually right above the sine button. You'll see it right above. Keep in mind that arc sine is an angle, isn't it? Arc sine is an angle. It's the angle whose sine is x. Let's do some examples. Let's compute some inverse trig functions. Okay. This is fairly difficult sometimes because you have to backtrack to trig values in order to find the answer. For instance, what is arc sine of a half? What is arc sine of a half? Well, here's what we're really asking. Can you think of an angle whose sine is 1/2? Sine of something equals a half. Now, what angle has sine equal to a half? Pi over 6. The sine of pi over 6 is a half, so the inverse arc sine of a half is pi over 6. And notice that pi over 6 lies in the correct interval minus pi over 2 to pi over 2. So we say arc sine of a half is pi over 6, and you can check that with a graphing calculator. I did that with my calculator, and the answer it gave me was approximately 0.523599. Now, some people would recognize that as being a decimal approximation of pi over 6. I'm not sure I would, but that is a decimal approximation of the exact answer, pi over 6. Let me reiterate. Lots of angles satisfy the equation sine theta equals 1/2. Lots of them do. But in this restricted interval, minus pi over 2 to pi over 2, pi over 6 is the only value. Okay, because we have to make this function 1-to-1. Let me make one other comment about the notation. I said that you sometimes write sine with a little -1 of x. That's an unfortunate notation. The reason being, you might think that means 1 over sine x. But 1 over sine x is cosecant, isn't it? It's not the inverse sine. So again, I personally prefer the word arc sine over sine inverse. But again, both are acceptable. Let's do some more examples. What do you think the arc sine of 0 is? Well, go back to the sine function. Sine of somebody equals 0. Sine of 0 is 0, so arc sine of 0 is 0. How about arc sine of -1? What would the arc sine of -1 be? I need some angle whose sine is -1, and that angle has to be in the proper domain, that restricted domain. Minus pi over 2, right. Arc sine of -1 is minus pi over 2 because sine of minus pi over 2 is -1. You can see how this works. You have to really be good at trig values to be able to evaluate inverse trig values. Of course, there's some good news here. These are built into your calculator. Let's do another one. Trick question coming up. What's the arc sine of 2? The arc sine of 2. All right, let's think about it. I need some angle whose sine is 2. But wait a minute. The sine function is always in that sandwich between -1 and 1. It can never get up to 2. So it's undefined. Arc sine of 2 is undefined. On a calculator, when I punched in arc sine of 2, the calculator didn't break. It just gave me back a message saying non-real result, or non-real. Now, what does it mean here? Well, remember we talked about complex numbers a long time ago? Well, it turns out that arc sine of 2 actually has a value if you're allowed to use those complex numbers. But we aren't going to do that. So for us, arc sine of 2 is undefined. Let's graph the arc sine function. Now, here are some of the features to keep in mind. First of all, arc sine of 0 is 0, so it's going to pass through the origin. It goes through the point 0, 0. Now, the domain is -1 to 1, and the range is minus pi over 2 to pi over 2. Let's plot a couple of points, and I'm going to do it sort of backwards. I'm first going to figure out what the sine function gives, and then I'll translate it to arc sine. The sine of pi over 2 is 1. So on the graph of the sine function, pi over 2 comma 1 is on the graph. So for arc sine, 1 comma pi over 2 will be on the graph, and here you see it on the graph, 1 pi over 2. That's the high point of the arcsine graph. And then it passes through 0, and it's an odd function, just like sine is an odd function, so you get that bottom point at -1, minus pi over 2. So that graph is the mirror image of the sine curve restricted to its smaller domain. Isn't that interesting? It's kind of an interesting curve, I think. It's a little short thing because the corresponding sine curve was cut off between minus pi over 2 and pi over 2. All right, we've defined inverse sine. There are 5 more trigonometric functions. I'm not going to go through all of the definitions and play with all of them, but let me just point out some of the ideas of developing the other inverse trig functions. And in particular, later on, we'll see kind of a puzzle come up. Let's look at cosine. How could we define inverse cosine? All right, well, I've drawn a graph of the cosine function here, one of our old friends, up and down, up and down. It's not 1-to-1. We have to do some restrictions, don't we? What would be a good interval to select to make it 1-to-1? Well, how about 0 to pi? On that interval, and it's indicated in green on the graph, on that interval, indeed, the cosine graph passes the horizontal line test, doesn't it? It didn't pass it on the full range of its domain, on the full domain, but by restricting it, it's 1-to-1. So, here is the definition of arc cosine. Y equals arc cosine x if and only if cosine y equals x, and here come the restrictions, x is between -1 and 1, and y is between 0 and pi. 0 and pi that's the restriction we made. The x part, -1-to-1, that's because it's still going between -1 and 1, like cosine always does. Here's a graph of arc cosine x, cosine inverse x. Notice some of the key points. You might remember that cosine of pi over 2 was 0. That means that arc cosine of 0 is pi over 2. You reverse the points when you do an inverse. You might remember also that cosine of 0 is 1. That means arc cosine of 1 is 0. And you see it there on the graph. Kind of a funny looking graph, isn't it? But that actually is the mirror image of our restricted cosine graph that we looked at a little bit earlier. Let's turn to tangent. This is perhaps my favorite inverse trig function. Here's a picture of tangent x. Tangent, you remember, has those repeated kind of curves there. It has those vertical asymptotes at pi over 2, 3 pi over 2, minus pi over 2, minus 3 pi over 2, etc. All right. First item. Is it 1-to-1? Not even close. Horizontal lines hit this curve infinitely often. Let's restrict the domain. Same pattern here over and over again. Let's restrict the domain. What would be a good domain? Well, I think everybody would vote for minus pi over 2 to pi over 2. And now that's an open interval, isn't it? Because minus pi over 2 and pi over 2 are not in the domain of tangent. But it'd be the open interval. That would be a good chunk to select. And on that open interval, tangent is indeed 1-to-1. Imagine just erasing the rest of the tangent graph and being left with that middle piece. So what's the definition of arctangent? Well, I think you know the game. Y is arctangent x if and only if tangent y equals x, and now we have to flip the domains and ranges. So let me think about it. The range of the tangent function is -infinity to infinity. So the domain of arctangent is -infinity to infinity. In a similar fashion, the domain of tangent was minus pi over 2 to pi over 2, the restricted domain, And hence, that will become the range of arctangent. Domain turns into range, range turns into domain. So there's the final definition of arctangent. Now, what do you think its graph's going to look like? What do you think the graph of arctangent is going to look like? Well, let's go back to tangent. And again, we're focusing on that single piece there in the middle. Notice it has two vertical asymptotes. Well, the inverse then will have two horizontal asymptotes, won't it? By symmetry. Isn't that interesting? So we'll have a couple of horizontal asymptotes here. And in fact, here's the graph of arctangent x. It's an odd function. It goes through the origin just like tangent did. And that's a mirror image of the tangent graph on its restricted domain. And notice those horizontal asymptotes at pi over 2 and minus pi over 2. Interesting, isn't it? Yeah. This graph, by the way, this function arctangent comes up all the time in calculus. It's amazing. It plays a big role in calculus. We can't see that yet in a pre-calculus course, but you have to trust me. Trust me. I'm not lying to you here. This function is a biggie for calculus. Okay, let's step back and do some computations. Make sure we're comfortable with these definition of inverse cosine, inverse tangent. What would the arc cosine of square root of 2 over 2 be? What do you think? Square root of 2 over 2. Well, we're asking the following question. Can you find an angle, some angle, whose cosine is square root of 2 over 2? Cosine equals square root of 2 over 2. Oh, pi over 4. Yeah, that's a 45-degree angle. That is arc cosine of square root of 2 over 2. How about arctangent of minus 1? Okay, I need some angle whose tangent is minus 1, and it's in the proper interval. And the answer, right, minus pi over 4. Because tangent of minus pi over 4 is minus 1, and minus pi over 4 is in that restricted interval minus pi over 2 to pi over 2. You can check this on your calculator, and you'll get those answers. And you can also check it on the graphs. If you look at the pictures, you'll see that these answers make sense. All right, good going. I think we're pretty comfortable now. Not only calculating trig values, but reversing it and calculating inverse trig values. It's difficult. Success in calculating inverse functions requires a certain skill with trig values themselves. So let's be the teacher for a moment. Student comes up to you and says, Professor, I think arc cosine of minus 1 is minus pi. And here's why I think that, teacher. Cosine of minus pi equals minus 1, right? And I would answer the student, you're right. Cosine of minus pi does equal minus 1. So the student says, and hence, arc cosine of minus 1 must be minus pi by the inverse property. What do you say as a teacher now? Well, first you encourage the student. You're right. Cosine of minus pi is minus 1. But that doesn't mean that arc cosine of minus 1 is minus pi, because minus pi is not in the restricted domain, is it? Remember, we restricted from 0 to pi. In fact, arc cosine of minus 1 is equal to pi. So, close, but not quite the right answer. Okay. Let's use these inverse properties to simplify some expressions. And remember how we did, for example, e to the log x, and we observed that they canceled each other because of the inverse property, so e to the power log x was just x. Well, the same things happen here, but of course we have these domain restrictions that make life a little more uncomfortable. So here are the rules. Sine of arc sine of x equals x, and arc sine of y equals y, if, and this is a big if the x values are between minus 1 and 1, and the y values are between minus pi over 2 and pi over 2. You have to be in those restricted domains in order for these properties to be true. For instance, what is sine of arc sine of 1? Well, this is a composition of two functions. First you do arcsine, and then you do sine. And 1 is in the proper place, isn't it? It's between -1 and 1. So the two functions cancel each other. You don't have to do any work. Sine of arcsine of 1 is just 1. The composition comes back to where you started from. How about sine of arcsine of a fifth? It's equal to a fifth. No problem. Now, you could have done this a different way. You could have said sine of arcsine of 1 can be evaluated because I know what the arcsine of 1 is. The arcsine of 1 is pi over 2. Why? Sine of pi over 2 is 1. So arcsine of 1 is pi over 2. And then the sine of pi over 2 is 1. I'm back to where I started from. You can't use that argument with the arcsine of a fifth. Let me say it this way. If I meet somebody who knows the decimal approximation of arcsine of a fifth, I worry about that person. That person needs a hobby. Arcsine of a fifth is some weird decimal, and you wouldn't know what it is, I don't think. But I do know that sine of arcsine of a fifth equals a fifth by the inverse properties. Let's do a tricky problem. Here's a common pitfall with manipulating inverse trig functions. Let's suppose we want to evaluate arcsine of sine of 3 pi over 2. At first glance, you might say to yourself, oh, arcsine and sine, inverse functions, cancel, I'm left with 3 pi over 2. Sorry. What's the problem? Do you see the issue here? 3 pi over 2 is not in the correct interval, is it? That interval was minus pi over 2 to pi over 2. In fact, if you evaluate arcsine of sine of 3 pi over 2, here's what you get. First, you do the inside portion, sine of 3 pi over 2, and that's minus 1. Sine of 3 pi over 2 is minus 1. And then arcsine of minus 1 is minus pi over 2. Isn't that interesting? So you can't just blindly assume these inverse functions cancel each other. You have to be very careful with the domains. And again, I admit, this is non-trivial. Okay. Let me show you an example in calculus books. We've done the inverse sine, the inverse cosine, and what I think is the most interesting function, the inverse tangent function. Well, there are 3 more. Cotangent has an inverse, secant has an inverse, and cosecant has an inverse. They don't play as big a role in pre-calculus as do those first 3. That said, the inverse secant function does occur in calculus a little bit. I mean, if I were to rank the importance of these inverse trig functions, I would go inverse sine, inverse tangent, inverse cosine, inverse secant. And let me talk about the inverse secant a moment. We aren't going to dwell on this. This is something that's not going to be important in our pre-calculus course, but it comes up in calculus in a very interesting way. I think you'll enjoy this. It comes up with me a little bit personally because I'm a textbook author, and you'll see an issue that I'll present here that actually impacts the way we write our textbooks in calculus. Let's look at the secant graph. Let's savor the secant graph for a moment. Here it is. We graphed it a lecture ago. We noticed that it was kind of based on the cosine graph, and it has these chunks, these pieces, and it has vertical asymptotes at minus pi over 2, pi over 2, 3 pi over 2, etc. So let's play the inverse game. Is this function 1-to-1? No, not even close. None of the trigonometric functions are 1-to-1. So it's not 1-to-1. It does not pass the horizontal line test. We have to restrict the domain. And this is an interesting choice. Which pieces of the secant function do you want to keep to make it 1-to-1? Well, there are 2 schools of thought. Some authors choose the piece from 0 to pi over 2, and then the piece from pi over 2 to pi. Others choose the piece 0 to pi over 2 and then pi to 3 pi over 2. Both choices give rise to a one-to-one function. That's not the problem. But these are different choices. And believe it or not, calculus books don't agree on this. About half the calculus books do one choice and the other half do a different choice. As a textbook author, we do the first one. We do 0 to pi over 2 and then pi over 2 to pi as our choice of the restricted secant function. And one of the reasons we do it is it seems to be what the graphing calculators are using. But the other choice is equally as good. And as an author, I've received many letters on this issue. Professors writing me and saying, why did you choose this restricted domain and not the other one? And I have to try to answer that. Both are correct. It's not like one is wrong, but they're different. Kind of interesting, I thought. Okay, how about an application? Let's do an application to rockets, say the space shuttle. And imagine the following scenario. I'm here with my camera, and over there, the space shuttle is taking off. Okay? And let's assume I'm 750 meters from the launch pad. That might be a bit close, but I'm protected. Okay, and as the space shuttle goes up, my camera angle will change as I'm watching the space shuttle. So its distance from the Earth, from the ground, is changing, and my camera angle is changing. Okay, so let me ask some questions about this scenario. Here's kind of a picture of it. I'm 750 meters from the launch pad, and the height of the shuttle I'll indicate with the letter S, and the angle that the camera makes with the horizontal we'll call angle theta. Let's write theta as a function of S, the angle as a function of the distance the shuttle has traveled. And then we'll find this angle for certain values of S, say 400 and 750 meters. So here we go. In the picture, do you see a relationship between theta and S? Well, I do, yeah. Tangent theta is S over 750, isn't it? That's the original definition of tangent, opposite over adjacent. So that means theta is arctangent of S over 750 using the inverse tangent function. Tangent theta, S over 750, arctangent theta, theta equals then arctangent of 750. So now I've expressed theta in terms of S using the inverse tangent function. Let's plug in a couple of values. If S is 400, then arctangent of 400 over 750 reduces to arctangent of 8 over 15. That's approximately 0.49 radians, which if you change over to degrees is about 28 degrees. It's not much of an angle yet. How about 750? When S is 750 meters, then arctangent of 750 over 750, oh, that's kind of nice. That's arctangent of 1. Arctangent of 1. That's an easy one, isn't it? Tangent of pi over 4 is 1, so arctangent of 1 is pi over 4, or 45 degrees. Now, when you go on and take a calculus class, this same problem will appear, but it'll be juiced up a little bit. You'll then calculate, if you know the speed of the space shuttle, how fast is it rising, you'll be able to calculate how fast the angle of the camera is moving. Because the camera will be moving, and you'll be able to calculate the change in the angle. Won't that be interesting? But that's a calculus topic now. All right, good. I hope you've enjoyed this brief look at inverse trigonometric functions. They rely so much on our knowledge of trigonometric functions. And again, some are more important than others, etc. Let me focus one more time on what I think is perhaps the most important part of the arctangent function, and that is those two horizontal asymptotes. Remember, tangent has vertical asymptotes, so arctangent has horizontal asymptotes at minus pi over 2 and at pi over 2. How could you check that? How could you check that pi over 2 is really a horizontal asymptote? Well, try this with your calculator. Calculate arctangent of a big number, say 1,000. Punch that into your calculator. If you calculate arctangent of 1,000, you'll get a number like 1.5697963. Do you recognize that number? Well, it's very close to pi over 2, isn't it? Pi over 2 is about 1.5707963. So you see that arctangent, as you go out to the right, is getting closer and closer to pi over 2. Pi over 2 is a horizontal asymptote. All right, great going. We'll pause now our study of the inverse trig functions and go back to the trigonometric functions themselves. And now, next time, I'd like to talk about what we call identities. We've seen some. For instance, at the most trivial level, the tangent was sine over cosine. That was perhaps the definition of tangent. And then we saw the fundamental identity, sine squared x plus cosine squared x equals 1 for all x. Well, we'll explore some fatter identities, some more interesting identities, larger trigonometric factors and trigonometric expressions that we'll be able to simplify using facts from trigonometry. So see you next time.